Hi everyone. In the previous lecture, I gave the idea of increasing, decreasing, bounded, and convergence of sequences. Now I want to mention about infinite series. Let me first ask this question. Is it possible to have a number for the sum of infinite numbers? Or does it make sense to have a numerical value for an infinite sum? Okay, let's answer this question. Consider this infinite sum 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus and so on. And I claim that the sum of these infinite terms is equal to 1. Let me give a simple proof. Now consider a square with length 1, as you see, and the area of this square is, of course, 1. Okay, so the area of half of this square is 1 over 2, and the other part is also 1 over 2. If you divide the rest, you will have 1 over 4, and the upper part is 1 over 4. If you divide the upper part, this part becomes 1 over 8, and the other part becomes 1 over 8. If you divide the rest, you will have 1 over 16, 1 over 16, and the upper part is 1 over 16. If you add them, all these areas, 1 over 2, 1 over 4, 1 over 8, 1 over 16, and so on, if you add them up, then you will finally have the area of the square, which is 1. So the addition of these infinite numbers is also a number. So we can assign a numerical value to an infinite sum, and we denote an infinite sum by sigma notation. This sigma notation depends on a variable like k, n, and it starts from a numerical value, let's say 1, and it goes to infinity. Of course, we must have a sequence for an infinite series. So how do we explicitly write this infinite sum? For k equals 1, you have a1. It is the first term of the sequence, ak. Second term of the sequence for k equals 2. Third term of the sequence, and it goes to infinity. Okay. This notation is called sigma notation. And then the other important notion is Sn, and partial sum of the sequence. Assume that this infinite sum is given from 1 to infinity, then and partial sum of the given series is denoted by sigma notation as k from 1 to n. Since it is n partial sum, we have n here, of course, for the sequence ak. What does it mean? For the first term, for k equals 1, you have a1. Then for k equals 2, you have a2. And for the last term, that is n, for k equals n, we have an. So this is n partial sum of the sequence, of the series. This one. Okay, let's write the first term of the sequence as 1. K from 1 to 1, since you have 1 here. It means k starts from 1 and the last term is also 1. So this is a1. S2, summation from 1 to 2, sequence ak, a1 plus a2. Third term is 3, summation from 1 to 3, 1 to 3, ak, a1 plus a2 plus a3. Okay, using the same idea, you can get the whole formula of Sn. a1 plus a2 plus a3 plus an is equal to n partial sums of the given series, as it is given in this definition. And the important result is that we say that the series from 1 to infinity ak converts to a number L, and we write this is by this equality if limit of n partial sum Sn is equal to that number. So if the limit of Sn exists when n tends to infinity, then the given summation also converts to that number, exactly that number. It is very important result. This is why the notion of n partial sum is very important to solve infinite series problems. Let's look at this example. Let the sequence an be a convergent sequence. So if it is convergent, let me express this result. If the sequence an is convergent, when n tends to infinity, an must go to a number, let's say L. Okay? Show that the rest of the question, show that the telescoping series, this kind of series is called telescoping series, show that this series is convergent and the sum of this series is equal to a1, which is the first term of the sequence an, a1 minus limit an. In this case, we show the limit of an by L, so we have to show that the sum of this infinite sum is equal to the sum of this ak minus ak plus 1 is equal to a1 minus L. So it's our aim to show this equality. And as I told you, since an is a convergent sequence, limit of an must go to a number, let's say L. Okay? And another important result is that if an is convergent, if an goes to a number L, okay, an plus 1 also converges to the same number when n tends to infinity. It is also another important result of the convergence of the sequences. So using these two results, we will solve the problem. Okay, let me write Sn for the given telescoping series. Sn k from 1 to n. Don't forget, we don't write infinite anymore. Ak minus ak plus 1, ak plus 1 is equal to, for the first term, for k equals 1, we have a1 minus a2. Okay. For the second term, for k is equal to 2, we have a2 minus a3. For k is equal to 3, we have a3 minus a4, and so on. For k equals n minus 1, this is the term before the last term, an, let me write down here, plus the term before the last term, for k is equal to n minus 1, k an minus 1 minus an, you write n minus 1 instead of k here, and finally for k equals n, an minus an plus 1. Okay, now if you cancel all these terms, finally you will have the first term minus the last term. Okay, a1 minus an plus 1, and this is equal to a1. Okay, we are looking the limit of Sn. This is Sn itself. Limit of Sn is equal to limit of a1 minus an plus 1. Okay, when n tends to infinity. Limit of a1 is a1 itself, since it does not depend on n, so it is independent of limit, minus limit of an plus 1 when n tends to infinity, of course, and this is equal to a1 minus limit of an plus 1 is equal to L. So as you see, since limit of Sn, limit of n partial sum is equal to a1 minus L, the given telescoping series converts to the number a1 minus L. So we proved the equality. So I will solve some extra problems about this kind of telescoping series using the idea of n partial sum.